All right, here we go. So in today's physics lesson, we're going to be learning about standing waves primarily. And before we do though, we need to talk quickly about what are called boundaries. All right, so I'm going to read at you for a second, and I apologize. All right, so first of all, a boundary. All right, so here's what a boundary is. When a wave travels from one medium to another, we say that the wave has encountered a boundary. All right, and when this happens, at least one of two things is going to happen. All right, first of all, reflection might occur. All right, some of the wave's energy bounces back into the original medium. All right, and then the second thing that might happen is what's called refraction. All right, in refraction, some of the wave's energy continues on into the new medium, and it experiences, a change in speed, right? Because the medium determines the speed. All right, in both cases, the frequency of the wave is unchanged. Okay, so what does all this mean in English? All right, well, here are some simple examples. So you've all seen Bugs Bunny cartoons or some sort of cartoon where the characters are in the mountains, and somebody shouts real loud and it causes an avalanche, right? Okay, so when you're in the mountains and you shout real loud, two things happen. One, there's an echo, right? You go, hello, and then a moment later you hear, hello, right? So that echo is an example of reflection. Okay, what happens is you shout hello, the sound travels through the air, hits the mountainside, so now the sound is traveling from air and it encounters a boundary, right? And the new medium is snow on the side of the mountain. And so what happens is some of the energy bounces back off of the snow into the air, and a little bit later you hear that sound as an echo, right? Okay. The second thing that can happen is some of the energy gets transferred into the new medium, right? Some of the sound waves get transferred to the snow, right? And so now the snow starts vibrating and you risk having an avalanche, right? Okay. So this idea is going to be way more important when we get to light, okay? And it's definitely more apparent, more noticeable with light, okay? But it does happen with all waves, okay? So there you go. Now, so the next thing we need to talk about is standing waves, all right? So standing waves, when a wave travels through a medium that has a fixed length, sometimes the incident and the reflected waves, remember those have the same frequency, they interfere in a way that gives the illusion of the wave standing in place, all right? And the frequencies for which this occurs are called harmonics, all right? And how the standing waves look depend on the boundaries of the medium, if they are fixed or loosed. Fixed or loose, sorry. And sometimes people will say closed instead of fixed and open instead of loose, okay? So let me show you all of this by using this little simulation that we've been using, all right? So first of all, let's talk about boundaries, right? So in a minute here, I'm going to create waves on this little simulation here, right? This little arm is going to vibrate up and down, and it's going to create waves that are going to be sent down the end to the vise, right? Okay, so the idea here is our medium is, red beaded string, right? Until when the wave gets here, the medium changes, right? Now the medium, when it gets over here, is vise, all right? So what's going to happen is when the wave travels down here, some of the wave is going to get transferred to the vise. So the vise would shake a little bit, right? But it looks like the vise is pretty sturdy. It probably won't shake that much. It probably has a fair amount of mass or inertia. So it's not really going to move significantly, all right? But the important thing that I want you to notice is that some of the energy will reflect back, all right? So let me show you that just by doing just a simple wave pulse, all right? So there we go. All right, so the wave goes down and reflects back, right? And every time it changes medium, it reflects, right? Okay, now it happens that the wave also inverts when it reflects. We'll talk more about that later. But at this point, what I want you to understand is some of the energy is reflecting, okay? Okay, so why do we care about all this? All right, so in a minute, I'm going to turn this arm on, so it'll start oscillating, like I said before, and what'll happen is some of the energy will travel down. It'll encounter a change in mediums, right, because there's a boundary there. I guess I should have said that the other way around. It'll encounter a boundary because there's a change in mediums there. And so then the energy will reflect back, and then the same thing's going to happen here. And the energy is going to kind of keep bouncing back and forth, right? But at the same time, we're going to be adding in extra energy here because the arm is going to be vibrating up and down, and it gets very complicated, all right? So let's take a look at what that looks like, all right? So I'm going to go ahead here, and I'm going to turn up the amplitude. Here we go. All right, so you can see that the wave is traveling down, right? All right, but it's complicated, right? Like every part of the wave is moving in different ways, right? And to me, it sort of looks like the wave. I feel like I can kind of see the energy traveling. Oops, I can kind of see the energy traveling this way, but then sometimes it looks like you can kind of see it coming back. All right, and so anyway, the energy is moving around, right? Okay. Well, remember, in a standing wave, what happens is at certain frequencies, the wave will give the image of standing in place. And when that happens, it's called a standing wave. All right? And so here's what that looks like. So it turns out that this particular string here that we're using has a natural frequency, which we will call F1. Turns out it has a natural frequency of 0.40 hertz. Okay? So what that means is if this was a guitar string and I plucked it, it would vibrate at a frequency of 0.4 hertz. Okay? So what I'm going to do is let's set the arm to vibrate at that frequency and see what happens. All right? And then I'm going to just sort of gradually boop, 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 increase the frequency a little bit and watch what happens. Okay? So what happens is it begins to look like a jump rope, right? And it doesn't really look like, to me, it doesn't look like the wave is going this way. I don't see the wave going that way. It seems to be just standing in place. All right, so this is what we call a standing wave. Okay? Cool. All right, now it turns out that this happens at different frequencies. Okay? It turns out that if you double the frequency, you get another one. All right, so let's do this again. I'm going to increase my frequency up to double it. So 0.4 times 2 is 0.8. All right, and then restart, and let's see what happens now. Oh, the pattern now is different, isn't it? So check it out. We've now got 3 points that are going to be called nodes. There's this point here, which isn't really moving significantly, except for a tiny bit because we have to maintain our vibrations. We've got a point here that's not moving, and we've got a point here that's not moving, right? So those points that I just marked, those are called nodes. All right, and what's happening at those points is this. There's a wave going this way, and there's a wave coming this way. In the last video, we talked about constructive and destructive interference. And what's happening at those blue points that are called nodes is you're always getting destructive interference. Okay? And so what's happening is the wave going this way at any given instant has some amplitude, and the wave coming the other way has the exact same opposite amplitude. And so, and at that point, I guess I should say. Okay? And so it cancels it out. All right? Now, these other points, here and here, that vibrate up and down, are called antinodes. And those are the result of constructive interference. So yeah, so the antinodes are caused because what's happening is those are points where, as the waves interfere, you've got constructive interference, okay? So, what's happening is, is you've got a wave going this way. At this point, you've got a positive amplitude. The wave coming back this way also has a positive amplitude. Those amplitudes add up, and you get this effect. Okay? All right, so I want you to notice, though, that these frequencies are special. Okay, so I used 0.4 hertz, and it worked. I did 0.8 hertz. Let's do 0.6 hertz and see what happens, okay? So if I do 0.6 hertz and restart it, you don't really get anything special, right? It just kind of vibrates. There are no nodes, right? There are no individual points that seem to be staying put, right? Okay, even if I increase my amplitude, you can really see it then. Oops, let me embiggen the amplitude. So it's nothing. It's just a big garbage wave, right? Okay, so we did F1, we did F2. So F3, let's triple our original natural fundamental frequency. Okay, so if we triple it, that's 1.2 hertz, right? 1.20 hertz, I guess, if we're being specific. All right, so here we go. Let's increase this guy up to 1.2 hertz. 1.2 hertz. Let's decrease our amplitude again a little bit and then restart it. Okay, and what you see now is there are 3 antinodes, right? Antinodes are here, here, and here. And then we've got nodes here, 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 and here, right? Okay? And it does occasionally die out because even though you've got constructive interference, you can still get an amplitude of 0. All right. So let's do one more frequency. Let's quadruple it. Let's go up to 1.6. And you can probably guess what's going to happen, right? So here we go. Let's increase our frequency. And so now we get 4 nodes. Well, I guess 5 nodes. Right? 1, 2, 3, 4, 5 nodes, and 1, 2, 3, 4 antinodes. Okay? All right, so that is an example of a standing wave. All right, now you can also have standing waves where the ends are not fixed. Okay, there we go. And let's decrease our frequency. This time I need it to be 0.2 because I've kind of changed my medium. All right, and restart it. So now we've got a standing wave, but the idea is now because it's open at this end, so at this end we've got a node, right? Because that point doesn't really move, right? Again, it's moving a little bit because of the way this app works, but all right, but you can see at the other end we've got an antinode, right? Because it's moving up and down. Okay, so this is at a frequency of 20 hertz, or sorry, 0.2 hertz, right? So that's our F1. All right, let's double it. So if I double my frequency, this time it actually doesn't work, and you guys will see why in a minute. But so if I double my frequency, watch what happens. This doesn't work. A little tedious waiting for it to get going. All right, but you can see every time there's a point that looks like it's going to be a node, it ends up moving a little bit, right? So there's no one point that seems to stay put. So it turns out that F2 doesn't do anything for us on this one. So let's put a little frowny face next to it. That one didn't do anything. Let's try F3. So that's going to be 0.6 hertz. Let's see what happens there. All right, so right, that's 3 times 0.2. Restart it. And watch what happens here. So here we're going to get a node, and then an antinode, and an antinode. Okay? So the reason that 2 didn't work is because there was no way I could have gotten a node over here. In a minute we'll do some drawings and you'll see that. Okay? So it turns out that F4 doesn't work, but F5 works. So let's show you F5. So 0.2 times 5 is just 1 hertz, right? Restart it. Now you get a node here, and a node here, and then antinode, antinode, antinode. So F3 works there. Okay? So, and it turns out that there's no way we can make an open end at the left end over here. So those are the only ones we can look at here. Okay, but it is possible that you could have both ends be open. Okay? All right, so anyway, so that's what standing waves look like. Okay? And the names of the parts, right? Nodes and antinodes. If you haven't written that down, you absolutely need to do that. Okay? So now let's attach some terminology to this and talk a little bit about what we saw. Okay, so terminology. All right, so we learned what a standing wave was. Okay? Looks like it's standing in place. All right, now the frequencies for which this occurs are called harmonics. Okay, so F1 is called the first harmonic, also called the natural or fundamental frequency. All right, F2 is the second harmonic, F3 is the third harmonic, etc. Okay, so once you know your fundamental, your first harmonic, multiplying it by any integer gives you that harmonic. So 5 times your first harmonic would give you the fifth harmonic. Okay, the frequency of the fifth harmonic. All right, so great. So it turns out that standing waves in a string usually have 2 fixed ends, like the first one we looked at, right? Okay, and so here's what the first harmonic looked like, right? It looked like that, right? And then it kind of oscillates between this position and this position, right? Okay, so we're going to use the letter L to represent the length of the string, the length of whatever is vibrating, okay? So your first harmonic looks like this, and notice that here, this shape here, that's half of a wavelength, right? Like to get a full wavelength, I would need another bloop, right? Another little bit like that. It goes down and then back up again, right? Okay, so that's only half of a wavelength. Okay, so it turns out then that we can kind of find this relationship. So here, the length of the string is half of a wavelength. That means usually you'll know the length of the string, but you'll want to find your wavelength, right? So it turns out that the wavelength is twice the length of the string. Okay? Now, in the second harmonic, look, the length of the string is exactly one wavelength. So the length of the string is 2 over 2 wavelengths, right? You've got sort of 2 halves, right? Each of these chunks is a half of a wavelength, right? So we have 2 halves, or 1 whole wavelength, right? So in the second harmonic, it turns out that our wavelength and our length are the same. Notice 2 over 2 is just 1, right? 2 over 2 is just 1. Okay? All right, so, and then in the third harmonic, look what happens. So here's a wavelength, right? My wavelength is now shorter than my string. So the length of the string is, let's count this up. There are 1, 2, 3 halves of a wavelength, right? Each little chunk is a half a wavelength, and this has 3 of them. So the length of the string is 3 halves of a wavelength, which means that the wavelength should be 2/3 of the length of the string, right? Oops, that's not what I wanted to do. Oh, my glob. Some troubles here. Okay, so, right, so if you divide this up into thirds, you need 2/3 to get 1 wavelength. All right? So, and then the nice thing is once you know your wavelength, usually you'll know the velocity or the frequency, and then you can use velocity equals frequency times wavelength to find the missing bit. Okay? So, and then just remember, the frequency of this first harmonic we're going to call F1. F2 is just 2 times F1. And then, oh my gosh, the third harmonic is 3 times F1. Okay? All right, so that's what it looks like if both ends are fixed. Now, sometimes you get what we had in the second example, where you've got one end fixed and one end open. All right, and it's basically the same idea. So here, here's your F1. Remember, we could only get the third ones, right? So here, F3 is 3 times F1. Over here, F5 is 5 times F1. So notice here, so usually a wave looks like this, right? And this shape here is just a quarter of a wavelength, isn't it? Right? This is just a quarter of a wavelength. All right? So here is our relationship. Here, the length of the string is a quarter of a wavelength, and therefore our wavelength should be 4 over 1 times the length, right? In other words, you'd need this length 4 times to get a wavelength, right? Okay? Over here, we've got 1, 2, 3 quarters. So here, our length is 3/4 of a wavelength, which means that our wavelength is 4/3 of L. And finally, over here in our fifth harmonic, we've got 1, 2, 3, 4, 5 quarters of a wavelength. So our length is 5/4 of a wavelength, which means that our wavelength is 4/5 of the length, right? Okay? So, and then I guess it's probably worth noting, look, here my wavelength got divided by 3, right, compared with this one. So the wavelength got divided by 3, and the frequency got multiplied by 3, right? Smaller wavelength, higher frequency. Okay? All right, and then the final one is you can have both ends of your wave be open. Usually this happens in a column of air. Okay, we'll talk about this. Most wind instruments are columns of air with one or both ends open. And so that's what that looks like. All right, and it turns out here you get the exact same relationships as if they were both closed. All right, because look, this is 1, 2 quarters, that's a half, right? So here our length is half a wavelength, which means that our wavelength is 2 times the length, right? Here we've got 1, 2, 3, 4 quarters. So our length is, did I do that right? 1, 2, 3, 4 quarters. Yeah, 4 quarters is 1 wavelength, right? Which means that our wavelength is just the length, right? Yeah, duh, sorry. This is 1 wavelength, right? Look, that's 1 wavelength. Okay. Over here, we've got 1, 2, 3, 4, 5, 6 quarters. 6 quarters is the same as 3 halves. And so our wavelength is 2/3 of the length. Okay. So that is that. And so then I guess just the main thing is when you're solving these problems, you just need to decide, which of these 3 possibilities is it? Is the wave being formed in a medium with 2 fixed ends, 2 open ends, or 1 of each? Okay. So we'll do some demos in class that'll hopefully clarify this, and there's a really cool lab that goes along with it that we'll use to calculate the speed of sound, rather. Okay?